Okay, let's look at our next topic, which is the atom. So if you go back in history, initially the atom came about because the Greeks believed that if you kept cutting something down and down and down like a piece of gold, eventually you get to a part that was indivisible. And that was basically the Greek word atomos. So that's what it initially was, atom meant indivisible. But about 1897, J.J. Thomson discovered a very, very tiny negative particle within the atom that was coming off a cathode. So he actually identified cathode rays as being this very small negative particle, which is eventually called the electron. Okay, so that negative particle then had to fit into the model of the atom, so the atom had to have something inside it which was negative. So he came up with what was called the plum pudding model there. So if you think of the plum pudding model as being like a positive pudding or a positive jelly, if you like, and inside that there were negative electrons or raisins, if you like, there. So after that, Rutherford had some scientists, Geiger and Marsden, doing some experiments with gold foil, with a very thin layer of gold foil. And what they were doing was firing alpha particles at that gold foil. And alpha particles have got a double positive charge. And the expectation was, if this is what the model was like, then as the alpha particles go past there, they should experience equal repulsion from the positive charges that are in the actual atom and equal attraction from the negative ones. So they didn't expect to be much deflection at all and just go through there in between the atoms. What happened though is that very, very large amounts went straight through, which meant that most of the atom was empty space. And surprisingly, a very, very small number actually were deflected at large angles, almost up to 180 degrees. Okay? So that meant that there had to be a big concentration of something repelling this double positive charge. So it meant that there had to be a concentration of positive charge somewhere within the atom. So Rutherford came up with the idea that the actual atom had a central nucleus, if you like, that was positive, and there would be something in there that actually hold it together because of these repulsions that were going to go on. But the electrons are a long way away, and the atom was mostly empty space. So that's the traditional model you would have had in junior science, that this positive nucleus in the centre, something gluing that together, if you like, and electrons circulating around that like planets around the sun, okay? And the electric attraction there was the force that kept it going in a circle, so it didn't just fly off. Now, this is really just history. What we're interested in at stage 2 level is the next level from there. So let's have a look at that next bit. So this evidence here was the electron discovery led to this one. The discovery with the alpha particle scattering led to the next model. And the next one had to sort of, I guess, account for other evidence that was around in the area of spectra. Now, the first part in the course says to be aware of continuous emission spectra there. Now, that's produced by incandescent solids or liquids. So you can think of lava or a hot filament there. So if you compare the frequency there with the intensity of the light that's coming off, you'll find you get a range of frequencies there, and the most common frequency at a certain temperature. All right. So this actually might be ranging from infrared frequencies all the way up to possibly red if it's glowing, and you see a red glow there. Now what happens is if you raise the temperature here and go to a larger temperature, make this the blue temperature there, what you'll find happening is you'll get faster vibrations of the molecules, and therefore a higher frequency EM wave is released as those charged molecules, if you like, oscillate at a higher frequency. So it starts to sort of shift like that. So you get a shift this way, and you start to get other colours involved, like red, orange, yellow, green, and if you keep going high enough, you'll get it to white hot, where it's releasing the full range of frequencies. Okay? So that's the continuous emission spectrum from red to violet you'd be aware of, and it sort of shifts to the right as you increase the temperature there. On top of that, you get line emission spectra. Now, it was known for quite a long while that there was a line emission spectra that was measured back in the 1800s. And we've actually done it in the lab already, where you actually attach an elemental gas like hydrogen or helium or neon, and you have a low pressure gas there, and you put it to high voltage. Okay? And electrons going through that there will actually excite the gas and release discrete lines of frequency that are characteristic of that particular element. You can also do it by getting metal salts and heating over a flame there. And if you look through either of those with a diffraction grating or a spectrometer, you can actually see the separated colours there. So something like this. Okay, so look at this one here. You've got red there, green, blue, violet in this particular element. But each element has its own line emission spectra. So the next model of the atom had to explain, why did you get line emission spectra going on for each of the elements there? Why did they only sort of release discrete energy values? And in actual fact, they only absorbed discrete energy values. So that was hard to understand with the model of the atom as they had it at the moment. So the model of the atom at the time was that the electrons were just going around in a cloud any old way around a central nucleus that was positive, and that was for all the elements. So the issue we had was, why was certain amounts of energy that were discrete being absorbed, and only a certain discrete amount of energy is being released in those lines and those particular frequencies, E equals hf. Okay, so that was one problem. The second problem was they already knew that accelerating charged particles were responsible for emitting EM waves. All right, and so a vibrating charged particle will release an EM wave because it was accelerating. If these are going in a circle, then they're accelerating. They've got a force towards the centre, and they're accelerating. Why are they not releasing EM waves as well, losing energy and then spiralling inwards and colliding with the nucleus? So it had a couple of problems with this model at the moment. So someone needed to change this model to try and explain why was that not happening and why was it only discrete, the absorption and the emission. So a guy by the name of Niels Bohr solved this idea by coming up with the idea of energy levels. So what Bohr said was, yes, you've got a central nucleus like that, which had a certain number of positives there. He actually proposed there would be neutrons or something, a neutral particle inside that was helping to glue it together. Now around there he said the electrons could only exist in certain stable states. Now the first of these states, which is the closest to the nucleus, would have the lowest energy because that was the most tightly bound. Because you've got to remember this is an electron, it's negative. To try and get that away from the atom, you have to do a lot of work to pull the negative charge away from the positive nucleus. So that has the least amount of energy. As you do pull this away to another level, and here's your next level here, which is stable, it's going to have a larger energy. The electron could not exist in between those two levels. So you could only go from one orbit to the next if it absorbed the right amount of energy equal to that difference. So you can actually sort of show lots of these levels here with an energy level diagram over here, which I'll do in a second. But just bear in mind that each of those levels is discrete, and as you go up they get larger and larger energy until you get to here, which is the ionisation point. Okay. Now at that point there, they've actually got zero kinetic energy, zero energy if they get there with a speed of 0, but they've escaped the atom. Okay. Now from here on, the energy can be any continuous amount there, continuous. Okay. But in between here, while bound by the atom, it's called discrete levels there, and there's an infinite number that and they also get closer together. Okay. So we can look at this energy level diagram here for hydrogen. So this is some of the values for hydrogen here. So these are the actual values in electron volts. Minus 13.6 is your lowest level. Now you would call that the n equals 1 level here, n equals 2, and so on, n equals 3. And as I said, they get infinitely close together until you get to here. This is your ionisation position then. And they can have any energy they like from there up. Okay, and that would be kinetic energy, essentially. But here they're bound. You can also have names for these levels here. This is the ground state. This one here, this is first excited state. Now how does that occur? Well, what has to happen is this has to absorb energy just the right amount to take the electron from the lower state to a higher state, because it can only exist in the first one, this first level, or the second one, or the others there. And I guess if you go back and look at the work by de Broglie, you can think of that first orbit there as being the one that fits in exactly one whole wavelength in its circumference. Okay, this one here fits in exactly 2 whole wavelengths for its circumference, and 3, and so on. So what you're getting here is when they come back on themselves, it actually comes back in phase and actually forms a stable orbit. So you can think of it as being an interference idea, okay, from the wave model. So what Bohr said was, we've got discrete levels, and the only way that the energy is absorbed or emitted is if you actually absorb the right amount of energy here, the difference between these two levels. Now you can represent these energy values here as energies above ground state. So if we call ground 0, it's actually easy to work with these values here because you know that this is a 10.2 level, 12.09, 12.75 electron volts above ground state, and 13.6 is your ionisation energy. So if the electron had been raised to a higher state by high voltage going through it, or by burning salts in flame, you would find that from that point there it could actually release a photon of this energy here, or a photon of this energy, or actually a combination of those two. You get 2 types of photons, or even a third type, or a big jump down. So but there are only certain possible photons it could emit, and that explained why there was line emission there. Okay, based on the fact because the energy levels are discrete, the absorption values could be discrete, and the emission values had to be discrete. So it really fit in very well with that. It also kind of explained why the accelerating charged particle was not releasing energy, because it couldn't actually just steadily drop down to different radii. It had to either be this radius or the one below that, a discrete jump there. So it kind of solved those two problems. So let's try and tie this together for the hydrogen atom, okay? So you've got line emission series going on whenever there's transfer of electrons going down from an excited state to a lower state, you get line emission. All right. Now bear in mind that if you want to go from an actual energy level diagram to an energy above ground state value, you need to just add 13.6 to each one of your values here, and that's the quickest way of doing it. So 3.4 plus 13.6 is 10.2. So that's how you calculate those if they're not given to you, because these are definitely easier to work with if you're trying to actually work out the values of photons absorbed or photons emitted. Okay. So the first series you can look at will be ones that actually go to the ground state directly. So this first one would be at 10.2 down, will give you a 10.2 electron volt photon, which would correspond to one line of emission in a line emission series, okay? And obviously you've got another one here and another one, and so you've got a whole series here that would finish in the ground state. Now this used to be called the Lyman series, by the way, but we don't use those terms anymore. It's the one that finishes at n equals 1. And that range between 10.2 and the biggest one will be 13.6 all the way down. So it's between 10.2 and 13.6. And what you'll find was if you could see these lines, you'd actually see them getting closer together as a series as it approaches the series limit there. Okay, the stop at the series limit. That's actually in the ultraviolet region, so you couldn't see those. That was not the first one discovered. So if you then try the other one here, there's one that finishes in the first excited state. It used to be called the Bohr series, the B series. Okay, and that energy range was different. That actually was from the first smallest one would be from 12.09 to 10.2, which is 1.81 electron volts, and the largest one would have been from the 13.6 down, which would have been 3.4. So you're talking about a range there of 1.81 to 3.4. And again, those lines will get closer together as it approaches series limit. And each one of these jumps here then corresponds to a line. Now this Bohr series was in the visible region. So the ones that finish here in this first excited state are all visible ones. So there's your first line of your visible, second line of your visible emission, third line, and there's your series limit for the emission series in the visible region. Okay. You've actually got another one above that, by the way, in the infrared there. So anything that finishes in this state here is in the infrared region because of low energy again. But again, they will get close together. So just bear in mind that each of those jumps corresponds to a line in the visible series there. Now, most of these questions are pretty standard then. If you were asked something like, what's the frequency of the photon present in the first emission line of the visible series, how could you work that out? So you've got to remember here that when there's an energy change then between two levels, and in this case we're going for the one in the first emission line of the visible series. Now the visible series doesn't finish here, that's ultraviolet. Visible series finishes here, so the first line in that series would be a jump that goes like that. Okay, so we're talking about a jump from the n equals 3 level to the n equals 2 level. So that's the levels we're talking about. That energy difference there between those two there is going to produce a photon when it drops down to the lower level. So that's going to produce a photon of HF energy. Okay, so when you do that, you're going to go minus 1.51, take away minus 3.4. Okay, so obviously that's going to be a plus there, so you're going to get a difference there. And the difference will be 1.89. Now that's in electron volts, so this is going to be your first trap. You need to make sure you convert that into joules before you get started. Now that's going to equal to HF. That'll tell you the frequency of that particular photon. So that's how you solve for F. You're just going to divide through by Planck's constant. Now just be conscious of some general terms as well. If they ask you for what is the first excitation energy, that's the energy needed to change the electron or raise it from the ground state to the first excited state. If they ask you for the ionisation energy, it's the minimum energy needed to raise an electron from the lowest state, the ground state, to completely be removed from the atom.